Hello everybody. Today we're going to be looking at math relationships. As you know, in physics, math is the language that we use to describe physical phenomenon. And there are three basic math relationships that we will be using on a regular basis. And in this lesson, you're going to learn about those three relationships and the shape of the graph that is produced when the variables in those relationships are graphed. Now, at the end of the lesson, every student should be able to identify the relationship between any two variables in an equation, and I'm going to show you how to do that. And every student should be able to identify and sketch the graphical representation of that relationship between those variables. Now, the first one you're extremely familiar with. This is the one they pound into your brain in Algebra 1, and that is the linear relationship, okay? In a linear relationship, of course, you're going to get a straight line. Yes, we know that, but let's go through some of the specifics and then see how it could relate to physics. So, first off, the form of the equation is y equals mx plus b. And in such relationship, here's what happens. When x increases by a factor, y increases by the same factor. Okay? So, in other words, if you double x, you're going to double y. If you triple x, you're going to triple y. If you split x in half, you split y in half. Now, let's look at some of the other information. X and y are your two variables, x being the independent and y being the dependent variable. And we'll talk more about that later. But what is m? Well, m is what we call the slope of the graph. Now, here's what you need to remember. Slope is nothing more than how steep the graph is. It's the steepness. Okay? Now, I know you guys want to say rise over run, but we have to be very careful about how we use rise over run. Rise over run is essentially correct, but in many algebra classes, you get used to counting squares on a graph and just using the number of squares. We can't do that in physics. Physics is based on measurements along the x and y axis. So we will be learning how to correctly calculate slope. Yes, it is rise over run, but we're not counting squares. Now, B is what's called the y-intercept. What does that mean? That means that is where the graph line crosses or intercepts the y-axis. So, for example, if you have a graphical representation of a linear relationship, it might look like this right here. And the steepness would be the slope, and there would be the y-intercept. If you have a negative linear relationship, it might look like that. Some examples of linear relationships in physics would be Newton's second law. All right, if we look at the form of the equation, it's the same as this one. Y equals mx. Y equals mx. In this case, you have an understood b of 0. So this would be the y variable, this would be the x variable, and the mass of the object would be represented by, oh, guess what? The slope. All right? So notice both the y and the x value are in the numerator. Neither one of them is squared, because that would make it a different relationship. So this is a linear relationship between F and A. Okay? Another example would be the distance formula. Distance equals speed times time. All right? Again, if we look at the d and the t, they're both in the numerator. Neither of them is squared. That's going to give us a linear relationship, and the slope would be the speed of the object. So y equals mx with an understood b of 0 at t equals 0. Okay? So you'll find that there are a lot of linear relationships in physics, and the variables all present themselves in this form. Both the variables are in the numerator, neither one is squared. That is automatically linear, okay? Now, let's take a look at the next relationship. The next relationship is, I better leave it there. The next relationship is another one you're familiar with, and that is parabolic. A parabolic relationship. Now, what happens in such a relationship? Well, when x increases by a factor, say you double it, you multiply it by a factor of 2, then y increases by that factor squared. So if you double y or double x or multiply x by a factor of 2, y is going to increase by a factor of 2 squared. If you triple x, y increases by a factor of 3 squared. If you multiply x by a factor of 4, y increases by 4 squared. If you multiply x by a factor of 1/2, then y changes by a factor of 1/4. So whatever x changes by, y changes by that factor squared. Okay? The form of the relationship, or the form of the equation of the relationship is y equals kx squared, where k is just a physical constant. I believe in your algebra classes they teach you that whatever that is, it can move the vertex of the parabola around on the graph, but it is a physical constant, okay? It's not a slope, because you can't find a slope for a parabola. Now, why can't you find a slope for a parabola? Because the slope is constantly changing. The shape of a parabola is a curve. And I would like you to notice that I'm only drawing half the parabola here. Now, why might that be? Well, it's because many times the negative side has no physical meaning. For example, if we were looking at an object accelerating and we wanted to look at the distance traveled versus the time during the acceleration, well, time is never negative, so you wouldn't have this side of the graph. So that's why I'm only drawing that half of it. What if you have a graph where x is increasing faster than y? In other words, you have maybe a square root factor. All right? Here, y is equal to kx squared, but right here, what if you had y equals x equals ky squared, and y is still on the y-axis? Well, you're going to get a sideways parabola then, okay? Either way, it's parabolic. Notice the form. Both variables, x and y, are in the numerator, but one of them is always going to be squared. You might actually even see a square root. For example, what if you had let's see, y equals the square root of x. Okay, well, to get rid of the radicand, we would square both sides. And guess what you end up with? You end up with a sideways parabola. You end up with a parabolic relationship. So if both variables are in the numerator and one of them is squared, that's how it's different from linear, then that is parabolic. Some examples would be, let's see, the distance equation when accelerating would be d equals 1/2 a t squared. And we're looking at specifically the d and the t. The 1/2 a, that being the acceleration, that's our physical constant k, all right, for uniform acceleration. So if we double the time, we're going to get 4 times the distance, okay? Another example would be the period of a spring, a mass on a spring. You get 2 pi on the square root of m over k. And if, and not the same k as this one right here, this is a spring constant k. So watch out, they use k a lot for different constants. But in any case, we're looking at the m and the t. Now, how do I know that's parabolic? For the same reason right here. If we square both sides to get rid of the radicand, we're going to get a t squared here. Get rid of the radicand, and you're left with m. So you'll have t squared is proportional to m. So that would be parabolic also. All right, so now we can see 2 relationships. All right, here, linear, both are in the numerator, neither one is squared. In parabolic, both are in the numerator, but one of them is going to be either squared or square rooted. That's going to be parabolic. All right, now, what about the last relationship? Let's take a look. The last relationship is hyperbolic. Or your algebra teacher may have said inverse relationship. Okay, so what happens in such a relationship? What do the variables do to each other? Well, x being an independent variable, then when x gets larger or increases, the y value decreases. Okay? When one goes up, the other goes down. Except in this case, we need to say increases and increases because the elevators only go up and down. All right? So as x gets bigger, y gets smaller, and vice versa. As x gets smaller, y gets bigger. Now, what form of equation would allow that to happen? Well, it's easy. Look right here. The form of an inverse relationship is y equals k, some physical constant, over x. Now I think you can see if this is a constant and you divide larger and larger values of x into that constant, the result is smaller and smaller values for y. And if x gets smaller and smaller, you go into decimals or fractions and divide smaller and smaller values into k, the quotient y would get larger and larger. Okay, so what would that look like? Now, basically, a hyperbola looks like this. Okay? That's the graphical representation of a hyperbolic or inverse relationship. And the one thing you need to notice is that x and y can never have a 0 value. Okay? And that's the answer to this question right here. Why can they never have a 0 value? Because it would be undefined. So having a 0 value would be undefined, because you'd end up with a 0 in a denominator, and you know that's not good at all. Now, just out of curiosity, I want to know what happens to these sides as they go closer and closer to the x-axis if they can never be 0? Well, they just continually get closer and closer and closer and closer, but they never actually touch the axes. In fact, if you remember, the names for these arms as they go further and further out, getting further and further, getting closer and closer to the axes but never touching, those are called the asymptotes. If you remember that unusually weird term, asymptotes. Okay, now what are some examples of hyperbolic or inverse relationships? Well, there is one perfect inverse relationship we will be eventually looking at, and that would be the definition of, or the relationship between period and frequency of, say, a pendulum or a mass on a spring or a wave. Period and frequency are true reciprocals of each other. If you know one, you simply reciprocate and you get the other automatically. All right? Another relationship would be the relationship between mass and acceleration. So look here, if I take Newton's second law, F equals ma, and solve for the mass, I get F over a. Okay? Now, in this case, we're looking at T and F, but right here I'm looking at M and A. Okay? If you push a car with the same amount of force, all right, and but the car gets more and more massive, so maybe somebody loads it up with suitcases, for the same amount of force, you're going to have less and less acceleration. Okay? Now, both of these are hyperbolic. Now, how can you just look at a formula and know that two variables have a hyperbolic relationship? Well, it's easy. Just look. It's completely different from linear and parabolic. In those two cases, the variables remained in the numerator on each side. Here you have one in the numerator and one in the denominator on each side. And when that happens, you know it's going to be hyperbolic or inverse. In fact, look at this formula right here. Now, this is an interesting formula. This is the formula for centripetal force. It is describing a mass traveling at some speed v around a circle of radius r. Okay? So this is an object traveling around a circular path. Whoops, I'm running out of room there. Let me push it over a little. There we go, circular path. Now, what we can do is we can look at the relationship between the force needed to maintain the object's circular motion and each of the variables. For example, what if we look at F and M? Well, if we look at the force and the mass being whirled in a circle, okay, I usually in class, I actually like to show a mass on a string and I whirl it in a circle. But if you have bigger and bigger masses, what happens to the force in the string that's needed to keep the mass moving in the circle? Well, notice both are in the numerator, but neither one is squared, so that is a linear relationship. So that means as the mass gets bigger, the force has to get proportionately bigger. If I double the mass, I double the force. And notice that's keeping the speed and the radius constant, because you can only change one independent variable at a time to see how it affects the dependent variable. So keeping these two constant, but changing the mass, we get a linear relationship. Now, let's keep the mass and radius constant, and let's look at how fast we're whirling the mass on the string. Well, notice F is in the numerator, V is in the numerator, but V is squared. Well, by definition, that was our parabolic relationship. Okay? So as V increases, F also increases, but by the square of the factor of V. Okay? Now, last one. Let's keep the mass we're whirling and how fast it's moving constant, and let's change the radius of the circle it's moving in. Now, if we do that, notice F is in the numerator, R is in the denominator. That's just like up here. That's going to be hyperbolic or inverse. Okay? In that case, as the radius increases, the amount of force needed to keep the mass moving in a circle decreases, or vice versa. If R decreased, F would increase. Okay? So that's how we look at formulas and determine the relationship that's going to exist between any two variables. We look at the form, just like I did here. And if we can determine if it's going to be linear, parabolic, and hyperbolic, then that means we can predict what's going to happen to one variable when another is changed. Kind of cool, huh? All right. Thanks for listening. Bye-bye.